also use the rules of exponents to simplify expressions that contain variables and exponents. One of the key rules that you'll want to remind yourself of is that negative exponents don't necessarily tell us to do any operations that involve a negative number. Rather, negative exponents are a reminder that we should engage in repeated division, just like as positive exponents are an indication that we should engage in repeated multiplication. So every time we see a negative exponent, that's an indication that we should use that variable base as a divisor and no longer as part of the product. G to the sixth will remain in the numerator as a positive exponent, but F to the fourth and H to the second will both move into the denominators as repeated divisions. This is what we would consider to be the simplified version of our original question, as it contains no negative exponents. In our next example, we have a series of different variable bases that match in the numerator and the denominator. So we've got x's in the numerator and the denominator, we've got y's, and we've got z's. Looking first at the 27 over 18, you can think of every part of this expression as its own separate individual calculation or individual simplification. So every spot for those repeated variables from the numerator and the denominator can be sectioned off and thought of individually. When we do this, we simplify each one of them one at a time. 27 over 18 simplifies to 3 over 2. X over x to the fourth simplifies to 1 over x to the third. Y squared over y to the fourth is 1 over y squared. And z to the third over z is z squared over 1. Each one of these variable bases that we just simplified comes from the fact that there were more x's in the denominator than there were in the numerator, more y's in the denominator than there were in the numerator, and more z's in the numerator than there were in the denominator. In order to finish, we put these products to get back together, multiplying all of the numerators together and getting 3z squared, and then multiplying all of the denominators together, getting 2x cubed y squared. In our last example, we share some characteristics with the previous examples, but we now also have this extra concern of an exponent on the outside of this larger expression in both the numerator and the denominator. That exponent applies to every base that's on the inside of the expression. So everybody, negative 3 to the fourth, m to the negative 1 to the fourth, n to the third to the fourth, and p squared to the fourth. Everybody from the numerator gets that fourth power. Just as we did for the numerator, we'll do the same thing for the denominator. Everybody in the denominator gets that second power. We're careful to put parentheses around each one of the base exponent expressions from each part because we want to make sure that we're grouping the exponents correctly and that every base from the denominator gets that negative 2. You might recall from your work in Algebra 1 that base to a base, an exponent to raise to another exponent means we multiply those powers together. So negative 3 to the fourth isn't going to change because that's the only power that's there. We multiply each one of those bases, of those exponents, and we do the same thing with the denominator. Every set gets multiplied together. In the previous example, we looked at the idea of sort of sectioning this off and then looking at how many more of each variable was there in each location. We can do that, but that becomes a little bit trickier when you have negative exponents in both locations. So for example, like with the m's. The other way to do this would be to subtract the exponents in each one of the cases. So -4 minus -6, 12 minus 2, and 8 minus 4. And fortunately for us, they all end up being positive. -4 minus -6 is going to leave us m squared. 12 minus 2 leaves us n to the 10th. And p to the 8th minus, or excuse me, 8 minus 4, p to the 8th over p to the 4, it just leaves us with p to the 4th. We have a trickier situation here. We can't do this in this first part because we have those two bases that don't match. We're not able to just to subtract this 4 and that -2 because the -3 and the 2 don't match. So we instead say, I know -3 to the 4th is going to be part of my answer. There's nothing to simplify with that. And this negative exponent tells me that this needs to become repeated division. Well, how do you divide a division? If you do that, that's going to turn that back to the numerator and instead make it a multiplication. So our final expression, written here in green, is the simplified version of what we started with. No negative exponents in our final answer. We were fortunate that each one of these subtractions ended up being positive. But that was only after we unraveled those exponents that were on the outside. We did power to a power for each one, and then we were able to simplify from there.